Okay, let's continue the discussion about isolated singularity. So we just introduced a removable singularity. And now let's see the theorem. Theorem says if f has an isolated singularity, at A, then A is a removable singularity if and only if the limit z approach A, z minus A times f of z is equal to 0. Okay, so this is an if and only if, a characterization of a removable singularity. Okay, let's see the proof. The proof is very, very good. So suppose f is analytic in the punctured disk. Centered at A. So you have a disk centered at A with the radius r, but you remove A. You remove the center. Okay, so that's this is from the isolate. From isolated. Then define g of z is equal to f of z if z is in this punctured disk, and 0 if z is equal to A. Okay, so we just define this g over this open disk. Because, sorry, here is the z minus A. Sorry, z minus A times f of z, this exactly this function. Because this limit z approaching A, z minus A times f of z is 0, we have that g is continuous over the disk centered at A with radius r. Okay, so it's a continuous function, and we will show that g of z is analytic over the disk BAR. Okay, so this is what we're going to show. We show that g of z is analytic. If we finish the proof, if we show this statement together with g of A is equal to 0, there is an analytic function h of z such that g of z is z minus A times h of z, right? So we know that for analytic function, if it has a 0, then you can factor out z minus A, so that h is analytic. It's important, h is analytic. And over this punctured disk, z minus A is not equal to 0. And we know that g of z is equal to z minus A times f of z. So we get z minus A times h This is true over the whole open disk, not just punctured. But over the punctured open disk, z minus a times h, which is g, is equal to z minus a times f of z. And because you remove a, so z minus a is not equal to 0, so h of z is equal to f of z. H of z is equal to f of z around a, and h is analytic, so this implies this implies a is removable. This implies a is removable. Okay, so that's the strategy to show that point A is a removable singularity, because h is that analytic function of the analytic extension of f. Okay, so the main thing is to show that g of z is analytic over the open disk. Okay, so in order to show that, so far we only know that g is continuous. Of course, g is analytic on the punctured disk, because g is z minus a times f. F is analytic. So here is analytic and continuous at the point. So to show that g is analytic, we will apply Moreira theorem. Moreira theorem involves triangular path. Okay, let T be a triangle in this BAR. Triangle in the BAR. And let delta be the inside of T together with T. Okay. So, for example, case 1. Triangle is here. It's T, this is delta. Case 1. If A does not belong to this delta, the triangle region, then T is this T is homotopic to 0. Why? You can shrink it to a point, homotopic to a point. It is homotopic to 0 by Cauchy theorem. The integral of g along T is equal to 0. Right? It just crash this triangle to a point. Then you can have the integral equal to 0. So case 2. Case 2, this triangle has one vertex as a point A. A, B, C. So A is a vertex. A is a vertex of T. A is a vertex T. Let T be A, B, C, A, A, B, C, A, back. So it's closed path, A, B, C, A. Okay. Then we choose a point X on AB, choose a point Y on AC. We connect X and Y. So let X belong to AB, Y belong to CA, and form the triangle T1, A, X, Y, A. So this smaller triangle. This larger one is called T. The smaller one is called T1, too smaller. And we only consider this smaller triangle, then there is a polygonal path. Let P be the polygon. Polygon, what is a polygon? Polygon is a X, B, C, Y, X. X, B, C, Y, X. Okay, so you see here in the T1, X, Y is from X to Y, X to Y. In the polygonal path, it's from Y to X. So we know two things. We know, one, this polygonal path P is homotopy to 0. And two, the integral of not f, g. The integral of g along T is equal to the integral of g along T1 plus integral of g along this P. Along T1 and along P. Right? Because here you actually have this additional segment. The other part belong to the original integral. Only this piece is has additional segment, but it counted twice. One is upward, the other one is downward, so they cancelled. So together these, we get the integral of g along T is equal to the integral of g along T1. So we can cut this big triangle to a small triangle. So here you see here we didn't give any additional condition about x and y. So x and y can be arbitrarily close to A. You always have such a thing, right? Okay, so that's the current situation. And now we know that G is continuous. G is continuous. And G of A is equal to 0. Is continuous to 0. Then for any epsilon greater than 0, for any epsilon, x and y can be chosen, x, y can be chosen such that the GZ is ops value is less than or equal to epsilon over L for any Z on L1. T1, sorry, for any Z on T1, where this L is the length of T, original T. It is the length of the original T. Okay, so it's tiny. So when Z is close to A, it's close to 0. So you can draw a small disk so that every point from that disk has ops value, the value less than absolute value of the value less than epsilon over whatever fixed number. This is a fixed number. It does not depend on the anything. It just depends on the original triangle. Okay, so hence the integral of t is equal to g over t is equal to integral over g over t1. Then we put ops value, and this one, see, put the triangle, we move the ops value into the integral. And this one is less than epsilon over L, and integral T1 dz. And this is a length of T1. The length of T1, from here we can see the length of T1 is smaller than the length of L. So it's less than, this one is equal and less than epsilon. So this ratio is less than 1. Okay, so this is the length of the smaller triangle. Okay, so what we get? We get this quantity is going to be less than arbitrary, this non-negative number is less than arbitrary epsilon. Hence, the integral of g along t has to be 0. The main step for the process is to cut off this large polygonal path. You see, originally your triangle could be very huge, but you can just select x and y so that for the integration purpose, this polygonal path can be ignored. So you only consider the tiny triangle. For the tiny triangle, the continuity works. Okay? So this is a case 3. 1, A is a vertex. And then that's case 2. And case 3 is that this is center, and you have the x, y, z. You have the triangle delta containing this A as an interior point. So if A in delta is inside T, not on the boundary, not a vertex, it's inside T. T, let's call it x, y, z, x, has vertex x, y, z, x. Okay. And now we connect xa, ya, and za. Xa, ya, and za. And you will see that the integral along the original triangle T is equal to the integral, assume you originally has a counterclockwise orientation, then it's equal to the integral of g along this x, y, a, x plus integral of g along y, z, a, y, y, z, a, y plus integral of g along zx, a, z, zx, a, z. Okay, zx, a, z. Let's check. So let's check. Here's ax, here's xa. So they are cancelled. Technically, you have two orientation. Here is down, here's up. So here's to the right, top, bottom. And here's up, here's down. So ax, xa, ay, where's ay, ya, and az, azza, yes, azza. So between them, they always canceled over the interval with a different sign. And except the interval, you will have three sides. So that's why you have this equality, And for each small triangle, A is a vertex of the triangle. A is always a vertex of the triangle. Then by case 2, we know that the integral of G along x, y, a, x is a small triangle. Its integral of G along y, z, a, y equal to the integral G along z, x, a, z, x, a, z. They are all equal to 0 because A is a vertex of this corresponding triangle. Okay, so this part, case 3 is actually the case 2 4 times. It's case 2 4 times. Okay, so for all three cases, we got the integral. We got the integral of G along t equal to 0. Then by Moreira theorem, G is analytic. G is analytic on the open disk centered at A with radius r. Right? So that's cool. It's a very, very good constructive proof. Okay? So in order to get an removable singularity, you just multiply it by z minus a and check the limit. If the limit is 0, then it is removable. It gives us an idea. For example, this is actually the big difference between the complex analysis and the real analysis. For example, in the real analysis, real calculus, y equal to opposite value of x is not differentiable. At x equal to 0. It's continuous but not differentiable because of the corner. But we know that if you have y, if you have this function times x minus 0, and you compute the limit, of course this limit is 0. So this condition cannot tell us this is removable or not. It's actually not removable. It's not a removable singularity. Not differentiable, it's a singularity, right? Okay, so this is hence in a complex analysis or complex calculus, there is no corner in this sense. If you have a corner is still well defined, then you multiply by the z minus a, then definitely will have 0. But there's no corner. This also tells us if f of z approaches infinity very fast, then f of z as x approaches a, then the limit z approaching a, z minus a times f of z may not be 0, right? You times 0, but this part is very huge. It's like the indeterminate form. Indeterminate form, one is 0, the other one is infinity. So it's like a 0 times infinity. Okay? If you have such a situation, maybe you don't, but you will definitely not have a removable singularity, right? If they approach very fast. So if f of z approaches some number, then this product will be 0. Then it's still removable. If it approaches a number, it's still removable. And if it's bounded, it's still removable. So if f of z is bounded around z equal to a, then a is removable. F of z is bounded, z minus a approaches 0, so this limit will approach 0 by the square theorem. So still it is removable. Hence, we have, after argument, we have the following definition. If z equal to a is an isolated singularity of f, then a is a pole of f if the limit approaches infinity. When it grows very fast, it may not be the product may not be 0, then it's not removable singularity, right? Okay, so here if it approaches infinity very fast, if it ops value approaches infinite, then it's called a pole. It's called a pole. This is the definition. Called the definition. So to translate this symbol into the epsilon delta language, that is for any m greater than 0, there is a number epsilon greater than 0 such that whenever z minus a is between 0 and epsilon, we have ops value f of z is greater than or equal to m. Okay, greater than or equal to m. So that's this part is just a translation of the limit symbol, and to have a pole, basically we just say the ops value approach infinity. To have a pole at singularity, ops value approach infinity. Okay. Okay. Sometimes this is not the ops value of f of z does not approach infinity. Sometimes it's not. It's 0, or it's bounded. It's not infinity. It's not bounded. So, if an isolated singularity is neither a pole nor a removable, neither pole nor a removable singularity, then it is called an essential singularity. Essential singularity. See, essential singularity means, okay, essential means no limit equal to 0. No limit equal to infinity. So this is essential. Okay. So which function has essential singularity? Well, first of all, which function has a pole? Pole 1 over z minus a to mth power has a pole z equal to a at d equal to a. Right? So you can use the modulus to prove that this limit is infinite when z approaches a. Okay, so this is an example. Essential singularity. Essential singularity, the author select exponential 1 over z. Exponential 1 over z. It's not a pole, it's not removable. Of course, we're talking about the 0. Why? Why it is not a pole, not removable. Not removable. You can it's unbounded, so it's not removable. And not let me see. Essential. Not okay, let's check this. For example, if I let 1 over z equal to x plus 2k pi I. 1 over z is x plus 2k pi I. K is 0, 1, 2, 3, so on. And just remember, we're talking about complex exponential function. So there's negative part, and also complex exponential function is a periodic. So this e to zk, e to 1 over zk is e to x fixed. And zk is 1 over x plus 2k pi I, of course, approaches 0. So what do we have? We have that this limit z approaches 0 of value e to what's that? E to 1 over z. At least if z is x plus 2k pi I, this is equal to e to x. It depends on the choice of x. Depending on x. But x can be arbitrary. So this limit is not infinity. This limit is not infinite, at least. Infinite. Actually, the limit does not exist. There's no limit at all. So it's not pole. Not a zero. Not a zero, I believe. What? You choose W as 1 over Z. Then when Z approaches 0, it means W approaches infinity. And even for the real case, you apply L'Hopital's rule, it is infinity. It's not 0, right? So the L'Hopital's rule. L'Hopital's rule here, you differentiate top and bottom, you will get infinite at least. So even in the real calculus, this limit is never going to be 0. So it's not removable and it's not a pole. So it's essential. It's an essential singularity. Okay, very good. Okay, so that's the other two definitions. So for the isolated singularity, we have removable. The limit is 0. We have pole. The limit of absolute value f of z is infinity. Not removable, not pole is called essential. So this is a complete classification. Complete classification. And in this part, this is a characterization. It's not a definition, it's a characterization. It's if and only if case. This is the definition. Okay? And now let's continue the discussion of a pole. Suppose F has a pole at z equal to a. F has a pole at z equal to a. So the limit z approach a, f of z is infinity. Then the function 1 over f of z has a removable singularity. At z equal to a. First of all, this definition could be very, the domain could be very small. We only know it is infinite at here. Possibly, we don't know if it's non-zero or not in the far from the A. So we just choose a small neighborhood. Removable, you only need a small neighborhood. Why it is removable? Because z minus a over f of z. You see this function. You don't even need z minus a. This limit is already 0. So 1 over f z has a removable singularity at z equal to a. Removable, then let h of z be this 1 over f of z for z is not equal to a, and ha is 0. Then we know that h of z is analytic in a neighborhood. in BAR for some R. BAR for some R. Okay, very small. I mean, we don't care. H of A is 0. It implies H of Z is equal to Z minus A to mth power times H1 of Z, with H1 of Z analytic and H1 of Z, H1 of A is not equal to 0. So we have multiplicity. We have multiplicity. And M is an integer greater than or equal to 1. Okay. So let's check. H of Z is 1 over F. So 1 over F is equal to Z minus A. Right? 1 over F is like this. So we switch them, we will get 1 over H1 over Z is Z minus A times F of Z. Be careful here. Whenever you write F of Z, this means Z is not equal to A. Z is not equal to A. It's not the center. It's not the pole. It's not the pole. It's not the pole. H1 of this is well defined. At Z equal to A, because H1 of A is not 0. H1 of A is not 0. This is well defined. So this means that Z minus A mth power times F of Z has removable singularity. It has a removable singularity. Right? Okay, so that's the study, the analysis. We have a pole. We get this removable singularity. And we have removable. Oh, this one has a removable singularity, means Z minus A times it has limit 0. Not itself approaches 0. It means Z minus A times it approaches 0. Okay? Okay, so what is the statement I want to present is the following. If G is a region with A in G, and if F is analytic, on G minus A with a pole at Z equal to A. If you have a pole, then there is a positive integer m, this m. There's a positive integer m, and an analytic function G from G to C. Here, this G is actually this 1 over H1 of Z. This is the G. This is a G, such that f of z is equal to g of z over z minus a to mth power. You see here, this is g divided by z minus a to mth power. You will get exactly this shape. Okay? So this is a statement. This is a statement. And actually, if you have analytic function with such, if you have a function analytic g and divided by z minus a to m, this one will give us a pole. If g of a is not a 0, then this is g of z approaches. Let me discuss it, explain. Okay, so put it here and you can see the whole picture first. So this is the page. Okay, it's a page. Then let's check. Let's see the discussion or the remark. If g of z is analytic and g of a is not 0. Analytic g of a is not 0, then the limit z approach a, g of z minus a to mth power, ops value, is definitely infinity, because g of a is a number over a 0 ops value, so it is definitely infinity. So this implies this function has a pole at z equal to a. Okay, so analytic function non-zero, so the numerator is a fixed number, denominator approaches 0, the modulus approaches 0, so it gives you the ratio infinity. And then by the definition of a pole, this ratio has a pole at z equal to a. So whatever rational function, whatever rational expression like this, it gives you a pole. And the proposition says if you have a pole, you can write it like this, right? So this is an if and only if situation. It's an if and only if situation. And what does it mean? What does it mean about what I write here? What I write here is this way. Is this. Okay, so if you have z minus a to mth power times f of z, limit equal to 0. If this m is equal to 1, if the m is equal to 1, at least 1, one satisfied, then this is removable. If and only if. This is if and only if. If m has to be at least 2, m is greater than 1, like this. Why? Because here, this is a multiplicity. Multiplicity is at least 1. 1 plus this 1 is 2. So this limit equal to 0 starts from 2. So when m is greater than 1, you have a pole. You have pole. This is also if and only if. And if this situation never happened, if the situation is never held, A is essential. A is essential. A is essential. So you just do the multiplication with z minus a times m. Z minus a times m. If this m can be 1, removable. If m has to be greater than 1, still you can get 0. That's a pole. If m, for whatever m, you don't have 0, this is essential. So, which means for any m, this limit is not equal to 0. You can never pull it to 0, pull it back to 0, then it's essential. It's essential. Okay, so in this place, we didn't emphasize g of a is 0 or not. G of a could be 0. That's allowed. For example, if you have a f of z equal to 1 over z to m, you can write z over z to m plus 1, or z over z to m plus 2, or z to k m plus k. It's okay. It doesn't matter. So for the characterization, all the formulas works. But for the quantity, okay, let's see, for the quantity, we have the following definition. If f has a pole at z equal to a, and m is the smallest positive integer such that f z times z minus a to mth power has a removable singularity, at z equal to a, then smallest, we emphasize it's the smallest, then f has a pole of order m at z equal to a. So we have an pole of order m. This order, when we talk about the quantity, we don't want this situation. We just want the first situation. But for the property characterization, is this a pole or not? All the cases work. Okay, and in order to talk about the pole for m, for this m, g of a is not equal to 0 in the proposition. G of a is not equal to 0, so you have to have such a thing. If g of a is 0, you can cancel something like this, for example, like this. So it's not smallest. It's not smallest. Okay. G of a is not 0. So assume that f of z is g of z over z minus a, and to m's power. G of a is not equal to 0. You assume we have such a thing, and this means that the order of the pole is m. Then G is analytic in this disk BAR. Then G of z can be written as sigma an z minus a to nth power, n from 0 to infinity. Okay, the power series expansion. Then what is f? F of z. So just divide term by term. You divide this power series term by term, you will have okay, let's read it here. A0 z minus a m, a1 z minus a m minus 1, z m minus 1 z minus a m minus 1 is a m a plus a m plus 1 z minus a, and so on. So this, after this is, we call it G1 of Z. We call it G1 of Z. Once you get the constant term, linear term, quadratic term, G1 of Z. And this is this G1 is analytic, where G1 from the open disk to C is analytic. So that's the definition. Let me quickly write it down. I don't know if I can finish it. This this part. Let me write a short part. This part. It is called the singular part. Of F at A. Okay, so this is on page 105. Okay, we stop. Thank you.